Hello everybody and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over the very first lesson in our evolution unit, but the beginning of the evolution unit is all about like geology. So we're doing a little detour into plate tectonics and also earth science. So to start with, this whole first portion is really going to be a lot of, like I said, earth science stuff, but a focus more on how the earth has changed over time and how we kind of know that. So just for basic information, right, the earth formed 4.5 billion years ago, a long time ago. And you may or may not already know the layers of the earth, maybe from middle school, maybe just from memory from something else. But if you do, you have a diagram in your notes, and you're more than welcome to attempt to fill that in. So, outer layer, we've got our crust, we've got our mantle, we've got our outer core, and we've got our inner core, right? These are kind of the main layers. During the formation of the Earth, the elements that were a lot heavier, like iron and nickel, they sank to form what became the inner and outer cores. So we're just going to refer to it as the core, even though there are two little sublayers here, but you get the idea, right? So we've got heavier elements are found down here. Then the lighter elements, things like silicon and like magnesium, they kind of floated because they're less dense. And so they're in this layer here, the mantle. Remember the mantle, even though it says it's like liquid, it's not like water. It's very, very, very viscous. So like, like really, 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 really thick honey, right? Like something that if you were to be able to like push on it, it would have a lot of resistance still, even though it's a liquid because it's quite dense. Keep in mind, by the way, that 4.5 billion years ago when the Earth formed, the Earth was essentially just a molten ball in space. So the outer layer, the crust, was forming and unforming and forming and unforming because the mantle was just so warm and so hot. But over time, because the vastness of empty space was so cold, that the mantle did solidify at the top into what we call the crust. Another kind of thing, though, right? So here's our larger version of this. If you haven't already in your notes, make sure you like color code the layers and then you label them as such. Just again, make sure you follow along in your notes as we're going through this. The center of the Earth is still really, really hot, even though it formed 4.5 billion years ago. The inner core and outer core and the mantle, but we're talking about the core specifically, is still very, very warm. It's so warm, in fact, that a lot of the different, kind of aspects of earth science that we're going to be focusing on all occur because of that heat that is still trapped, essentially, underneath the surface of the crust. So, again, just for labeling purposes, just know that the inner and outer cores are still very, very warm, and that by comparison, the crust is really cool. And just for again, a minor segue into a little bit of thermodynamics here, the way that heat travels is it always is going from a hotter object to a cooler object. So when people say things like heat rises and stuff like that, that's kind of what they're talking about, right? Is that we have this really warm area and this cool area. And so that means that the heat is going to always be moving from where it's hottest to where it's coolest. Okay, you have another diagram in your notes. So feel free, color code the continental crust, the ocean, and then the mantle underneath. Whatever colors you really wish, but like I'm using kind of red and then blue and then kind of a brown color, but you can use whatever you want. Keep in mind, right, that as the Earth is cooling, the crust is not cooling evenly everywhere, right? And so because it's not cooling evenly, there are places where the crust starts to crack, and essentially that's what forms the plates that we're going to be looking at and talking about. There are two different types of plates that the crust is made out of. Continental crust and then oceanic crust. So you can see again, continental crust that's highlighted here in kind of brown, whereas the oceanic crust is kind of just like this, like kind of zebra pattern, this little striped pattern here. But oceanic crust is much denser. So oceanic crust is kind of, you can think of it as, it has basically sunk to the bottom, right? So oceanic crust is kind of at the bottom, and it's a lot denser than continental crust. Continental crust is a lot lighter. And so you can kind of picture the continents as floating almost on this viscous mantle here. The oceanic crust is also floating, but notice like how much less dense this continental crust is. It's like a lot fluffier. That's how I'm going to describe it. Whereas the oceanic crust is not. It's a lot more compact. Okay, plate tectonics. Here is a simplified map of the different plates that the crust is cracked into. There's about 15 of them. Depending on which map you use, this is kind of a representation of the one that we're going to be using. There's around 15 major and minor plates. Obviously, if we were to zoom in on a plate like the North American plate or something, there are little cracks, like microscopic cracks here. So the plates are actually split up into subplates and even smaller plates than that, right? Like for example, right, like the San Andreas Fault in California, that is a part of the North American plate here, and you can't even see the San Andreas Fault because it would be like right over here. And it's like, you know, it's cracked from the North American plate. But again, 15 is around the number that we're going to be utilizing for our purposes. Keep in mind that these plates are floating on that mantle, right? So all of that like liquid magma-y stuff, that's what these things are floating on. So why do these plates move? So yes, the plates move. What's triggering that plate movement? It's convection. And so convection is just the movement of heat in a fluid. And a fluid can be a liquid or it can be a gas. And it's where hot fluid is rising and then cool fluid is falling. If you've kind of ever seen a lava lamp, that's a good representation of convection, where you have this like hot light bulb at the bottom and then there's no light bulb at the top. So you get heat moving up, and these little bubbles of oil are traveling upwards, and then they start to sink back down when they get cool. Here is a thermal map. So this would be the crust, like the very outside. It's that kind of like dark reddish area here. And then this would be where our core is, which, again, there's no data there right now for this map, and that's totally fine. But this whole area here is the mantle, this entire region here. And so you can see that we have this very hot kind of fluid moving almost like wisps of smoke or something. And as it hits the top of the crust, it cools off and it falls back down. And you get this kind of like circular pattern, and that's really what convection is all about. Now, what is causing the convection is the core is really hot and the crust is really cool by comparison. So without this temperature difference, we wouldn't get any movement like this. Okay. Now, there are 3 different types of plate boundaries, and those are just places where plates interact with one another, where they meet. So this is our very first one. So here we have these really like dark little trenches. They're oceanic trenches. And so this trench right here is one of the more famous ones. It splits the Atlantic Ocean kind of in half here. This is an example of this type of plate boundary. So my question is, what does divergent mean? Divergent means to separate, right? And so that's what a divergent plate boundary does. It's separating one plate from the other plate. And what's doing that is convection. So without convection, if the core was completely cool, or had completely cooled off in 4.5 billion years, then we really wouldn't get like these plates moving at all. There would be nothing to drive their movement. They'd be kind of stationary and stuck in place. There's a lot of different examples of divergent plate boundaries out there. The Atlantic Ocean is one of them. The Atlantic Ocean is growing in size because right from this like giant crack here, this is moving this direction on the left, and this is moving to the right on this side. So North America and Europe are actually getting further and further apart from each other. Iceland is this little island right here at the top, and it is being kind of split apart by the divergent plate boundary that is splitting the Atlantic Ocean up. And so Iceland is actually growing in size because every time that these plates are moving, magma is being released and new land is being made right in the center of Iceland. Here's an example. Okay. What about the opposite of divergent, right? So like think the Himalayas, Mount Everest. What's the opposite? Anybody have an idea? The opposite of divergent is convergent. So convergent plates are ones that are moving towards each other, and there's always going to be a winner and a loser for the most part in these types of interactions. So one of them is going to sink and melt, and that process is called subduction. So here you can see in this animation, subduction is occurring. That plate on the right is being crumpled and kind of moving downwards. The one on the left is being crumpled, but it's not moving downwards. In fact, it's moving upwards. So we're kind of getting mountains forming here. There are a lot of different types of convergent plate boundaries. So the first one that we're going to talk about, though, are the Himalayas. So India, in the Pangea kind of times, everything was together. And then as the continent started to separate, India was essentially an island that like crashed into this area of China here. And so that's what caused the Himalayas to form. It's two continental plates colliding with one another. Another good example of that, though, the Alaskan Peninsula. So these little volcanic islands here off the coast of Alaska and Russia, those are caused by two oceanic plates that collided with each other. Remember, oceanic plates are denser, right? They're more dense. So continental plates are a lot lighter. Oceanic plates are a lot denser. The last type, obviously, right, would be an oceanic and a continental plate kind of colliding, and that's how the Andean Mountains formed. So the Andean Mountains are these mountains here. We're going through Ecuador and Peru and Chile, Argentina, Colombia. And so all these little triangles that you see are volcanoes. When an oceanic and a continental plate form, again, we have a lot of mountains. So we have a very mountainous region. A winner and a loser, whichever one is the loser, kind of becomes the fuel for these volcanoes. All right, last type, transform plate boundaries. So transform plate boundaries are plates that are moving, I was going to say perpendicularly. That's probably not the right word for this. Parallel. They're moving parallel to one another, but they're scraping each other as they move. So this one's moving down, this one's moving up. Notice these little starbursty symbols that look like explosions. Those would be earthquakes. So transform plate boundaries, typically you have a lot more earthquakes in that area because when they're scraping together, that energy has to be released somehow, and you're not really going to get volcanoes because there's nothing fueling this movement. It's just they're scraping side by side. So the San Andreas Fault in California, great example. Also, though, the Dead Sea. So you have the Arabian Plate and the African Plate, and where they meet right here, you kind of get this movement that forms a transform plate boundary. And that's it. So if you have any questions, please let me know. Make sure you're filling in your notes as you go, though.